Hello, this is my makeup discussion for my AO5 discussion section for week 2. And for the first problem, I have air, these little air particles, within my piston cylinder. And there's also a resistor being stuck inside of it. Okay, so let's first talk about the piston itself. The piston has a mass of 100-pound mass. Also, an area. The surface area is 1 square foot. And the last thing we know about the piston is that there's atmospheric pressure being pushed down. And as we know, if you've done enough problems in English units, 14.7 pound force per square inch, psi. Okay. Now let's look at the air. The air has a mass as well. 0.6 pound mass. We're also given that throughout the course of this problem, where we go from state 1 to state 2, there's a change in volume. And the change in volume is positive. It is positive 1.6 cubic feet. The final condition we're given is that between both states, there's a change in internal energy. And the change in internal energy is 18 British thermal units per pound mass. Okay, we have everything that we need to go through this problem. Let's first start by talking about the first law of thermodynamics. And at least for this class, I believe it's change in energy of a system is equal to change in heat going in and out of the system minus change in work. And this definition for first law is one of the reasons why we say that, heat entering a system increases energy, heat leaving a system, decrease energy for system. But it kind of explains how we define work. What I mean by that is when work is positive, when work's being done, we're actually losing energy because of this minus sign. So that means when work is being done by the system, for example, expanding a piston, you're giving off energy into the environment. So that's positive work. Your system is doing work, but that results in decreased energy. Conversely, negative work value by minus sign actually means an increased energy. This means things like compression, for example. So when your system receives, when negative work happens to your system, it's kind of like receiving energy from the environment, like the environment compressing this system further, and you have more energy inside the system. So, it's a bit odd, because I believe in some classes like physics, this would be positive, and the definition is switched, but in our case, it is what it is. Okay, so I also should explain our objective. Our objective is that we want to solve for delta Q. So what is exactly delta Q? If we look at this resistor right here, that is our delta Q, because the resistor, when put into a circuit, I guess like a closed loop circuit, the resistor would heat up, and then that would add energy to the system through it in the form of heat. I also mentioned that work, as my explanation earlier with compression and expansion, is done based on that piston moving up and down. All right. Yeah, and let's actually start there. Solving for delta work. So I believe this equation has been shown many times, but integral with respect to volume is done here. So pressure times dV, we can get work. So an assumption that I will say now is we're assuming that this problem is quasi steady, meaning that the increment of dV is so small that our pressure can be treated as a constant. It can be treated as a isobaric process because the process is so slow. So slow that we're able to maintain constant pressure. End of the day, it's just this. And if we look at the PV curve, it'd be like a rectangle section. All right, so we have delta V, but we don't have the pressure term. That's what we gotta solve for. There's many different ways to get this P terms or to solve for this P terms. One example would be like the polytropic formula, and that might show up in the quiz. But at least for this case, we'll be looking at the the point of view or the approach of using a free body diagram. So here's our piston. So what forces are acting on it? One example is force from the air, the trapped compressed air that's pushing up towards the piston, causing that's like some form of resistance. And what is it exactly resisting against? One form of that is the force from the atmosphere, as well as the weight of the piston itself. And as usual, states 1 and 2 are, in some sense, like a steady state. The system is at rest. Therefore, we can use this following formula if I quickly define my convention. The net force in the y direction has to be 0. Net force would be force of air subtracted by force of atmosphere subtracted by the weight of the piston is equal to 0. And we can break down these force components into more simple components. In terms of the forces, we'd say it's actually the pressure times area and for the weight, it's just mg. Okay. So, one thing to point out is that the force caused by the air is, pressure times the area of the piston. That same pressure can be correlated to this pressure that we're trying to solve for, the pressure of the system trying to do the work. That's perfect. That's exactly what we need. So let me just move everything to the other side and divide by area of the piston. And we get this formula. And we have all the variables, so let's just plug it in real quick. I believe this is what's used for English units. Now, one of the reasons I picked this problem is actually the fact that unit conversion would be required in order to solve for this. And because not many people are used to English units. So we're going to try to keep it in terms of PSIs. Let me do a quick explanation of this as well. And if someone can fact check me, I'd really appreciate this because this is what I found online, and I believe it's true. And these are the 3 units you're going to see very often: pound force, pound mass, and slugs. This is a force value, and these 2 are mass in terms of units. Relying on dimensional analysis, I believe this is the conversion between these 3. 1 pound force is 1 pound mass times the gravitational constant. And 1 pound force is 1 slug times 1 feet per second squared. So I believe this is the correct relations between these 3 variables, or units. So we'll be plugging in here because we have a pound mass right here, and we don't want that. So dimensional analysis says that we plug it right here. Okay. So, fair enough. You get some nice things, some cancellation going out. End of the day, we should get something like this. Oh, we forgot feet and inches. We gotta split that up. Okay. So 1 feet squared, 144 inches squared. Okay, now it looks better. No wonder. Okay. My apologies. I just realized what's wrong. The piston is supposed to be 100. That's 100 pound mass. Not that. I put in air earlier. That's my fault. So, as expected, which is we would get 0.7 psi for that section for the weight of the piston. As a result, the pressure of the air must be 15.4 psi's in order to hold up the atmosphere and the weight of the piston. Okay. Oh, that's perfect. Now we can solve for the work. Where is my... Okay. Okay, well, I guess now we can take PSI and turn it to PSF. All right, and we get pretty big number. But to be fair, this is in terms of pound force per feet. We don't really want these units. If we look back at earlier, this component here, it's in BTUs, British thermal units. So I believe, if I remember correctly, it's how much energy is required to raise 1 pound of water by 1 degree Fahrenheit. I believe that's the unit being used at the time, and that is a British thermal unit. The translation between what we have and what we want is 778 pound force times feet is 1 British thermal unit. Okay, perfect. So if I divide by that value, I get 4.56 BTU. Okay, that's where I want. That's perfect. That's what we need. In terms of this equation, we have this. We don't have energy yet, but we can use internal energy to get to change the energy of the system. So to keep it really brief, change in energy can be expanded to like change in kinetic energy of a system, its potential energy, and a bunch of other stuff. But at least I believe that our system is at rest and steady state. Most of these things will be canceled out. All we gotta care about is change in internal energy. And this will change in future chapters, but at least for now, this is true. And that change in uppercase U is the same as mass times change in lowercase u, change in internal energy. Therefore, change in energy of the system would be the mass of the air multiplied by the change in internal energy of the system. 18 is BTU per pound mass. Okay. Rederiving, I guess, our first law of thermodynamics. We get the following equation. And a final result will be that little resistor thing inputted a total of 15.36 British thermal units. And that's fair. This number should be bigger than, should be the combination of these two, because our system was doing work. It was expanding. It was basically using its own energy to push that piston higher. So it's doing work. Yet still, the energy, or overall energy of the system is still increasing. You know, that's a little bit of contradiction. So how's that possible? And it's because that resistor is providing enough power or enough energy to complete those two actions. All right. And before we conclude, let's talk about the efficiency of this whole setup in the first place. And the efficiency term can be usually simplified down to the idea of how much work was able to be done based on provided input or energy. So our efficiency would then be which is like 29.7% efficiency, which is pretty standard for like most, I think, into their systems in general. Very, very like low efficiency values. So yeah, that is the problem of the resistor generating this piston cylinder of air. Next up, I'm briefly covering the power cycle and refrigeration cycle problem. Oh. Okay, so I have two reservoirs, a hot and a cold reservoir. I also have two systems. The first system is based on the power cycle. It takes in some kind of source, some kind of fluid with more energy and disperses that same fluid with less energy or a lot lesser power. And that transition between these two energy results in a work being performed by the power cycle. And that work accounts for the work right there that's produced. It accounts for the difference between the two reservoirs. Okay? That's the power cycle. Over here, with the refrigeration cycle, it's the opposite. It takes in the fluid at that has less energy, and given some kind of work or power, it's going to output the same fluid with to a place with higher energy, which is I believe if the zeroth law of thermodynamics is mentioned, it's that what was it? Substances move from hot to cold, but given work, we make the opposite happen. Okay, so let's talk about the efficiency values for both systems, because what I want to talk about, or what this problem is trying to get to, is what is the relationship between these two efficiency values. So let's start off with the power cycle, which is system A. Power cycle is about, the efficiency is based on the work that's able to be done based on the inputted energy, which in this case is the hotter reservoir. So hotter reservoir powers this system A, and work is done. And given our definition from earlier, we plugged it in. The refrigeration cycle is a bit different, represented by beta. And it basically, in this side, it's saying, given the initial energy input, which is usually colder, the colder side, how much work is needed to transfer this the colder substance to the reservoir of the hotter substance. All right, and one thing we quickly note is set some caps for power cycle efficiencies. Is limited to 1, where 1 is already like the idealistic theoretical case, and it can't be less than 0. Same thing for refrigeration cycle, but we will not talk about the upper limit for now, as it's not as relevant to our problem. Okay, so we have these two equations, and they have matching similarities, which is like the work part of it. It shares the same work, and if you look at the system, that's really obvious. The work being produced or generated by system A is being received by system B. Therefore, we can quickly solve for the work side of it and substitute it into the same equation. Okay. So as a result, we have this. And, it looks like a mess, but let's just start moving stuff over and see if we can figure it out. So eta A times beta B equal to QC over QH. So yeah, let's get rid of this part. And how can we do that? Well, if we didn't straight up just solve for this part right away, we could have simplified this equation and gotten it so that efficiency of the power cycle is equal to 1 minus energy at the cold reservoir divided by energy at the hot reservoir. So that's the factor that matches with our part down here. Okay, so I'm going to move all the efficiencies over. Oops. And factor out the eta. And this is the resulting relationship for this diagram I have right here. And does it make any sense? Yeah, I'd say so. Let me quickly explain. So let's start if, in our very idealistic case, where the efficiency of the power cycle is 1. Following this formula, in order for this equation to be true, the coefficient of coefficient of performance of the refrigeration cycle must be 0. What does that mean? Well, 100% efficiency means that all the energy from the hot reservoir going into this A system is all being converted to work. So basically, nothing goes to the cold reservoir. The cold reservoir, there's nothing going on there. Therefore, when it comes to the refrigeration cycle, it's taking all this work, but the input at the cold reservoir is nothing exists there. Therefore, looking at our coefficient performance equation, it'd be 0 divided by work, which is 0. That checks out what we have here. Let's quickly talk about at 50% efficiency. At 50% efficiency, let's just say that our hot reservoir is at 2 BTUs, and 50% efficiency means a 50-50 split. The cold reservoir will take in 1 BTU, or would be at 1 BTU, and the work being done would also be 1 BTU. So from the perspective of the refrigeration cycle, it'll then say, hey, my equation for the coefficient performance is input at cold reservoir divided by the work, which is 1 BTU divided by 1 BTU, and that would be, 1. And based on this equation, that's true too. 1/2 times 2, which is 1 plus 1, that equals 1. That checks out. And, we can keep going, and you'd, see some kind of trend, but yeah. End of the day, I just wanted to show the derivation process for using efficiencies for power cycles and refrigeration cycles. Okay, for the next part, we'll be looking at this homework problem, and particularly looking at part B, in which we evaluate this piston cylinder assembly from the perspective of the piston. What we're looking to find is the change in the work of the piston, as well as any change in potential energy. So let's start with the work first. The equation for the work, relative to classical physics, is integral of force and the distance. In our case, we're traveling vertically, so we're using z between state 1 and state 2. So we have our piston here, and we know, if we've done part A, that we see that the piston is going to move up, because as the gas is heated and expands, the piston is pushed upwards. So you know that there's going to be a positive change in the z direction. However, when we're integrating, at least for this piston, what is the force being done to the piston? And that comes in the form of gravitational pull, also known as the weight. So if you notice, these two vectors are pointing in different directions. When moving from between state 1 and 2, we're moving upwards, but the force is pointing downwards. And that dot right there infers the dot product. So because these two vectors are pointing in completely opposite direction, the work being done by the piston becomes an integral of negative of the weight of the piston integrated between state 1 and 2 of the height. So then we look at our new force bar diagram, which is has only two components. One is the force being done by the atmosphere, and the other is the force by the gas being compressed underneath. And if we were to look at our net force along the y-axis, we would get the following equation. And if you were to have done part A earlier, you'd recognize that this is actually equal to mg, which is the weight of the piston. So we're going to ignore this side for now and just look at this. So let's plug this following equation into our new formula. So it's negative, so we can switch this around. Evaluate the integral. There's no z terms, so we can say the following. We're going to further simplify this. That's just the change in Z. And finally, you say that the cross-sectional area of the piston multiplied by the change in height is just the change in volume of the overall configuration. Okay. Now if I plug in the values that I remember, it's like 1 bar minus 2 bars multiplied by, let's change in volume. I think it was like 0.02 cubic meters. Yep, I think that's right. So then I believe this should turn out to be negative 2 kilojoules. Okay, so that's the change in work of the piston. And does this match with our definition of work? And as I mentioned earlier, following this standard, yeah, it makes sense. So negative work, it infers that there's a positive increase in the overall energy in the system. And yeah, if you move an object higher up against the Earth's gravity, then there's more work that can be done, like a boulder on a higher hill versus a boulder on a smaller hill. Okay? And actually, speaking of this equation, let's break it down in order to find the change in potential energy. So at least for the time being, total energy can be broken down into kinetic energy, potential energy, and change in internal energy. So we know that, at least from the problem statement, if you read it, the gas takes in all the heat that's being input into the system. The piston doesn't receive any of the heat. So there's no heat transfer being done for the piston. The piston's moving very slowly. The term is like quasi-static. So we can ignore kinetic energy. It's moving very slowly. And once again, there's no heat being transferred into the piston. There's no temperature changes, so we ignore internal energy as well. So it gets a direct correlation where the change in potential energy is equal to the change in the work. And as we know, or negative change in the work, sorry. So therefore, change in potential energy is 2 kilojoules. And the whole point of this is to show that there's work needed to push against the atmosphere and work that is being used to be stored as potential energy. This is our last problem of today, and this is a problem I started for my first week of discussions, so I'll try to catch people up who haven't seen this problem before. But essentially, we start here. This is a closed-lidded container, and this closed-lid container of H2O is set on top of a Bunsen burner, and this Bunsen burner is then turned on, and then heat is being added to the system. And from this heat being added to the system transforms to where it's a mixture, a coexistence of two states of matters, liquid form of H2O and the vapor form of H2O, and it gets heated up, and then the composition will then change. And we're trying to figure out exactly what is the amount of heat being added to the system. That's what we want to know. So first, instantly, you should be able to tell that this problem is isometric, meaning that we have a constant volume that's not changing. And I guess additionally in this case, constant mass, because there's no mass being added in or out of the system. So therefore, these two constants are fixed. And I guess one thing you can do if you see mass and volume is instantly, it's like density, right? That's what you think of, it's mass for volume. But in the case of thermodynamics, we have this kind of weird variable. It's called specific volume. And specific volume is actually the inverse of density, and it means volume over mass. So I want to say volume over the mass. And that's what we have right here. And why is it important? I'll come back to there in a bit. So let's look at these three states I highlighted, states 1, 2, and 3, occurring at different places along the graph. But notice that they have fixed specific volume, but in the end of the day, it's just basically it has a fixed mass or fixed volume and a fixed mass is what I'm trying to say. So state 1, here's some conditions given that we found during week 1. State 2, here's some other conditions we found. And in state 3, we have yet to figure that out. So we want to find out, how much heat is added to get from state 1 to state 3. Okay. So I want to quickly talk about this little x term. I believe this is called the quality factor or quality. And so the idea of these steam curves is that given a certain temperature or pressure value, there is a corresponding temperature or pressure or temperature value in which two states of matters can coexist. An example of this is, imagine the boiling point for water for standard atmosphere, 100 degrees Celsius. So 100 degrees Celsius, water can then start to boil. Liquid water can boil into water vapor, but not all the liquid water can boil at once into vapor. It's a gradual process. Therefore, within that exact kind of state, at that pressure and a specific pressure and a specific temperature, two states of matters can coexist. And that's what leads to our quality factor. And so initially, we start with quality of 1, 0.5. This means that within this container, 50% of the composition is vapor form and 50% is still in the liquid form. At state 2, where this quality factor is now 0.731, 73.1% of the composition is vapor and only 26.9% is liquid. Finally, in state 3, quality factor is 1 and the entire thing is vapor. And it kind of correlates to this kind of like our position on the graph with respect to this right-hand side of the curve. And basically, when you hit the right-hand side of the curve, your composition will be all vapor. Whereas the left-hand side is where the composition is all liquid. Okay. So, off the gates, I just want to say that, isometric, we can instantly say that the work being done is 0. There's no change of work being done. That much is apparent. So that means the only variable left would be the change of energy. And our point question is, how can we figure this out? Okay, well, let's start at state 3. It's the easiest part. So at some point, we see here that our process converges into the right-hand side. That's why we can have a quality factor of 1. So when it converges, there's this one component that would match. And that component is our specific volume that I mentioned earlier. Okay, so later on, I guess either next week or in 2 weeks from now, you'll learn these things called steam tables. And these steam tables is how you get values that you want based on your specific volume, your pressure, your temperature, and other variables. So we know that the specific volume that we currently have, I guess at state 3 and state 2 and state 1, will be 0.8475 cubic meter per kilogram. And if you look at here, this gives a specific volume for the left and the right-hand side, and right-hand side of our steam, that little steam curve. And so, because we're looking at when our value converges at the right-hand side, we'll be looking at this specific volume of G for the vapor. And the vapor value, as pressure is increasing, it's going down, it's decreasing, and you see our value sits somewhere between here at the 2-bar mark and between the 2-bar mark and the 2.5 bar mark. So our value is somewhere between there. That's where our specific volume is. And correlating to it, we have the internal energy of that gas, and we have it at 2 bars and also 2.5 bars. Therefore, we can form a kind of ratio to interpolate what our internal energy is at the third state, or at state 3. Okay, so the ratio goes something like this. What we want to find minus the thing before that, and for us, it's the 2-bar, divided by the thing in front of it, the 2.5 bar, and then the thing behind. That's how I remember the ratios, and this is what we want to find. What we have is specific volume. So I'm writing this all for the gaseous form. Okay, let me plug in our values real quick. Okay, get the 2 bars. This is the value that I see. And for 2.5, I see this value. It's all in kilojoules per kilogram. Current specific volume. Okay. Specific volume before that at the 2 bar mark. Look at the one in front, the one behind again. So the idea is that we don't know the exact value of internal energy because it's not given by the table. The table's value is basically, consistent and true. And so we have to do something called like interpolation. We're interpolating to get the value in between using like this kind of slope method. Okay, anyways, we can then solve for U3. I'll plug into my calculator real quick and give us an answer. I get the following value, which should lie between the 2 internal energy points we had earlier. I'm referring to this 2. Should lie in between those 2 values. I believe it does. So at state 3, that is what we should expect for internal energy. Still, unfortunately, we need to go back to find the internal energy at part 1 in order to get the difference between the 2 parts. And then, essentially, we got to go through a very similar process here. And remember, it's an isometric process, so specific volume stays the same. Let me change some of our variables. Also, you need to go back to the table to determine exactly what's going on. Okay. So this time we aren't really doing an interpolation value. Now I think about it. I probably should get rid of the whole part. Okay. So the process to find the internal energy at part 1 is actually easier than I thought, or I remembered at least. So the process is actually go back to the steam table. So earlier we interpolated because we knew that our specific volume value lay between these 2 points, but we didn't exactly have it, right? So that's why we had to like interpolate between these two values. However, at least for state 1, we were given a very important value, and is that we know that the pressure there is 1 bar. The pressure at state 1 is 1 bar. So we can actually use our left-hand column, where it basically shows the pressure, and we fixed the pressure 1 bar. And by fixing the pressure at 1 bar, you can see that our internal energies, if the composition is a fluid or if it's a vapor, what would its energy be? And so we know that we have 50% of it is fluid and 50% of it is gas. Why? We're given that quality factor earlier, 0.5. So we can say that half of it will have this amount of energy and half of it will have that amount of energy. And we can get the kind of cumulative energy of our composition. So I believe the formula to do that is as follows. And I'm going to say just at 1 bar so we know what's going on. So I believe using this formula, you should be able to get U1. I'm going to plug in the values that we need real quick. Okay. And I plug into my calculator. Okay, we have the following internal energy for state 1. which also lays between these two values. So we know it's, about right. Okay. So let's get our change in energy because we have our internal energy values. I believe the mass was 5. No. It was not 5, 9. Okay. Take the difference between U3 and U1. What do I get? Okay. At 631.02 kilojoules. Okay, that's perfect. Oh, that's right. And now, our first law of thermodynamics equation that we're really familiar with, and then the work drops out, the change in energy caused by the Bunsen burner heating up is 631.02 kilojoules.